Good afternoon, everyone. Today, the Arab seminar has the great pleasure of welcoming Dr. Ismail Alkhatib. Dr. Alkhatib received his PhD in Chemical and Petroleum Engineer from the Khalifa University of Science and Technology under the supervision of Professor Lourdes Vega and Professor Mohammad Zaha. He is currently a research scientist in Chemical and Petroleum Engineer at the same university and a member of the REACH, Research and Innovation Center for CO2 and Hydrogen. His research focuses on applying molecular thermodynamics to multi-scale modeling to address environmental and energy-related challenges. This includes developing new materials for CO2 capture, sustainable refrigerants, and alternative pathways for hydrogen production and transportation. He works on creating low-cost solutions for reduced emissions, especially in heavy industries and advanced cooling systems. So once again, welcome Dr. Al-Hatib. Thank you so much for accepting the invitation. It's a pleasure to have you here with us. Please feel free to start your presentation.
Thank you, Yuan. I really appreciate the introduction. And first, I want to start by thanking everyone for the opportunity to be on this platform. Atom Seminar Series has been something foundational during my PhD journey. It was inspiring seeing all of these scientists and researchers apt in our field in applied molecular thermodynamics and learning from them. And then it's a pleasure for myself to be invited to this platform. Now, for today, I'll be talking about molecular thermodynamics, how it can become a foundational platform for advancing sustainable decarbonization technologies. But before we dig into the presentation and the content of it, I'll give you a tiny brief about where I work. I work in Khalifa University, which is in Abu Dhabi, in the Gulf region in the Middle East. It's a beautiful small city, but very modern. And I specifically work in the Research and Innovation Center on CO2 and Hydrogen, RICH Center, which is focused on 5 thematic areas. They are related to CO2 capture and utilization, hydrogen production and distribution and utilization, and also sustainable fuels. The center started since 2019, and since then it has an expansive network of stakeholder and international collaborators. Now, a small brief about myself. I'm originally from Palestine. I was born and raised in the UAE, and I work under the Red Center, of course, under the mentorship of Professor Lourdes Vega, who was one of the prominent speakers in the seminar series. I've been working as a research scientist for the past 2 years, and before that, a postdoctoral fellow. Now, my own personal research interests, I'll segregate it between tools and application. The tools are basically multi-scale modeling, trying to connect microscopic to macroscopic behavior, and of course, some integration of machine learning along the way. And all of this is applied to thematic concepts in sustainable decarbonization, which are related to CO2 capture, hydrogen production, and of course, sustainable refrigeration. Now, the first thing that we want to talk about is why molecular thermodynamics. Our own understanding of classical thermodynamics is something related specifically to macroscopic behavior. With classical thermodynamics, we understand how a system will start to behave when subjected to specific changes in specific state variables. And this concept started, as we want to say, under the work of Carnot and then the development of the thermodynamic laws. But that's not enough for us to see how the system behaves. What we want is to understand why the system behaves in that specific way, which takes us to molecular thermodynamics, starting with the work of the concepts of Gibbs and then popularized under the work of Prosnetz for the 20th century. And with molecular thermodynamics, we have a closer look into the microscopic scale. We start understanding why the behavior or the phenomena at the bulk for the bulk property will start to behave that way, depending on the type of molecules, atoms, and interactions that are governing the system. Now, how can molecular thermodynamics become beneficial for us in sustainable decarbonization? And for that, I want to point out everyone to this beautiful paper that was monumental in my own development from John M. Prosnetz, talking about the 3 dimensions of chemical engineering in the 21st century. And that puts at the forefront how molecular thermodynamics can connect 2 concepts and 2 aspects. The first one is a practical application. With molecular thermodynamics, you can complement experimental data by finding properties in a much faster way. Let's think about it as computer-based experiments. And then this data can help us in process design and scaling in a much faster way than experimental data. At the same time, it gives us that fundamental aspect because of the key word, which is molecular. So we start understanding why a certain system will behave in that specific way for a particular application on a microscopic scale. And that gives us the luxury to start selecting the system or even rationally designing them or engineering them for that given application, in a way complementing or guiding experimental efforts. Now, with molecular thermodynamics, it goes through a spectrum, a very particular spectrum. We have molecular dynamic simulations, Monte Carlo simulations, and of course, molecular equations of state. They govern different length scales and different time scales. So whenever we deal with a particular system, the question becomes what time scale and length scale do we need to deal with? And at the same time, what type of computational resources are required to understand that type of system and its behavior? Now, we will have a very focused overview, which is basically on an applied thermodynamic topic, which is how we can use this molecular thermodynamic platform to develop new solvents for CO2 capture. So the governing issue that we have is, this is something that everyone started feeling specifically in the summer, that the planet is literally burning. The summer became extremely unbearable with the level of heats that are increasing progressively. And all of that is because of the increasing level of emissions for CO2. And that comes in from the current energy economy, heavily reliant on fossil fuels. And with that comes in specific patterns of extreme weather changes. But then that would make the planet on the long run quite uninhabitable unless we do something that will depropagate the escalating level of CO2 emissions and their impact on climate change and global warming. There are different ways that we can cut these emissions. The easiest one that we can say is basically we have to increase the energy efficiency. In a way, we want to start generating more power from the fuel that we're utilizing for the same amount of CO2 that we're generating. Another option is that we have to switch to alternative non-carbon-based fuels or renewables, ones that are low carbon or zero carbon emitting sources, such as solar and wind. One last option is, of course, capturing the CO2. And reducing carbon emissions or capturing CO2 is something that is always pivotal whenever we start talking about net zero targets by 2050. For that aspect, we have to focus on carbon capture, utilization, and storage. And what happens with this CCUS value chain, we want a specific capture technology that is capable of capturing CO2 from either point industrial sources or even from the atmosphere, the ones that are already emitted. Once the CO2 is captured and recovered, it's transported in different means, and then for its inevitable either permanent storage, where we effectively get rid of the CO2, or conversion and utilization, and by conversion into value-added products that, in a way, will enhance the economics of the CCUS value chain. The most pivotal part of the entire value chain is actually the capture process, which is the most cost-intensive, and at the same time is the one that hinges on the sustainability of the entire CCUS value chain. So how can we capture CO2? There are two things that we need to focus on whenever we talk about capturing CO2. There is a material side and a process side. The material side is basically a specific substance that has a high affinity for CO2. It likes to be with CO2 and capture it. That can be in the form of a solvent, which is a liquid. It can be an adsorbent, which is a solid material. It can be a membrane that filters the CO2 from the flue gas effectively. And then once we have that particular material, we have to put it in a process or an engineering system to make the capture system continuous and operate at specific conditions that we can control. With adsorbents, we can use adsorption. With solvents, we can use absorption technologies. And of course, with membrane, we have a membrane process scheme. Now, in order to have a cost-effective CO2 capture system, there are things that we want on the material side and also on the process side. The material side, we want something that has a high affinity for CO2. It's a cheap material that is easy to produce, is safe to use, is green and sustainable from bioresources if possible. And at the same time, it's easy to recover and regenerate in the sense that we don't have to spend a high level of energy to recover that material and then use it continuously. On the process scale, you want the engineering of the process to be quite simple. You want the energy demand to be small, whether thermal or electrical. The process has to be efficient in recovering CO2, durable for a long-term utilization, at the same time, profitable if possible. Now, the focus is always on solvent-based CO2 capture, and that comes in from the idea that this is a mature technology. It's called an end-of-pipe technology. It has been utilized since the 1930s in natural gas processing for CO2 recovery and H2S removal. And with this technology, what happens is basically that you would have the flue gas emitted from a specific point source. It will be rerouted to an absorption column where the CO2 with the flue gas will be contacted with the solvent. The solvent will capture CO2 via weak interactions, and then it will recover it in the rich solvent over here. The clean or scrubbed flue gas without the CO2 can be emitted safely to the atmosphere, while the rich solvent is regenerated in a desorption column through the application of steam or thermal energy. The benchmark solvent that is typically used is monoethyleneamine. And surprisingly, that main challenge for solvent-based CO2 capture is actually the type of solvent itself. With the benchmark solvent that we have nowadays, it's quite toxic, corrosive, degrades easily, and then it requires a high regeneration energy. And that adds into the overall cost of capture. It makes the technology quite expensive to actually be deployed on scale. So what can we do at this stage to make better solvents? There are different strategies that we can take a look at. The first one is let's try to look at different molecular structures for these amine molecules. The benchmark solvent has a primary amine in the primary position. We can look at other structures that has secondary amines, tertiary amines, multiple or cyclic amines, or even sterically hindered. Some of these molecules have already shown some promise, but the regeneration energy remains questionable. Another potential is to change the formulation of the solvent. Traditionally, the aqueous amines are mixtures with water. You would have 38% of the amine and 78% of water. The challenge with the regeneration energy is actually the amount of water that we have. What happens is that water has high thermal properties, heat capacity, and enthalpy for vaporization. And that adds into the parasitic load of the regeneration energy. So the concept might be to change water and look for alternative organic co-solvents, such as alcohols or even other diols, for example, something that can easily evaporate without the high level of temperature. The last potential is to actually change the entire chemistry. Let's stop looking at these type of molecules in the traditional sense and propose alternative systems that can capture CO2. That includes specific types of chemically bonded ionic liquids and deep eutectic solvents. They're showing some promise, but at the same time, they have a high issue with viscosity. Okay, so with these different strategies, how can we actually look for new solvents? Traditionally, what we would do is we would perform lab scale measurements. In a very specific way, we'll figure out a new solvent formulation, test them out for specific properties. And once we have these properties and we're confident with the solvent, we'll scale the data so we can use it in process modeling and simulation, and then look at the performance of the solvent at scale. Once we narrow down the systems to a manageable pool, you would start doing some pilot plant demonstration at a specific higher capacity than what you would do with lab scale measurements. And then eventually, once you find something that's quite promising, you can start implementing it at an industrial scale. And this entire process is quite lengthy. And one of the lengthiest steps is actually the lab scale measurements, because you would need a rational way to guide you to specific solvent formulations. And at the same time, looking at these formulations, given the number of variables from temperature, pressure, even composition, will make the lab scale measurements quite extensive. And in this particular area, thermodynamic modeling and molecular modeling can help in the search for new solvents by expediting it and doing a more of a rational-based computer experiments that is built and grounded on physics. In order to do that, the most pivotal platform that you would require is to use an appropriate molecular model. In one of the slides that I mentioned earlier, that one of the questions is basically the length and time scale that you require and the computational resources. And for this type of application, because we deal with solvents, they're basically fluids and gases, the most appropriate one is basically a molecular-based equation of state. And the equation of state of choice is a variance on the statistical associated fluid theory, which was developed by Walter Chapman and Keith Gibbons and George Jackson, very prominent speakers that were involved in the Atom Seminar series. And the variant that we're working with is basically the soft-saft equation of state developed by Professor Lourdes Vega and one of her PhD students in '97. Now, the general concept of SAFT, just to make it a bit simpler, is that the entire equation is written for the total Helmholtz energy of the system, where you would have the ideal contribution, and that will ideal gas contribution, and with that you can get the residual. And then you would start perturbing a specific reference term that would describe the dispersive and attractive interactions for segments, and then adding all of these different molecular features to make the model for the molecule a bit more realistic. In the case of the soft-saft equation, we always work with Lennard-Jones segment reference term, and then we start perturbing it with different terms for the chain formation, which is covalent bonding, association term in case of hydrogen bonding, and then the polar term recently developed or added in the case of polar molecules that exhibit permanent dipole or quadrupoles. Now, the beauty of this equation is that it's a coarse graining model. You would have a representative molecular model for your molecule that you're dealing with. And with that, you can represent it with key specific features that makes the model a bit more manageable computationally. These parameters include the number of monomers or the chain length for the molecule. Whenever you deal with a spherical molecule, you can assign it a chain length of 1. You also deal with the monomer diameter, the dispersive energy, and then in the case of association, you would add 2 terms that would require association energy and volume. And then lastly, in the case of the polar moment, you would add the dipole moment and then the fraction of segments affected by the dipole moment. The beauty of this equation is that it's tied directly to classical thermodynamics. Because of the Helmholtz energy, you can use thermodynamic derivative to get other thermodynamic properties, for example, pressure and chemical potential. And then from there, you can add on other equations of other theories in order to extend the pool of thermodynamic properties calculated. Of course, the equation is extended to binary and multi-component mixtures with mixing rules specifically for the non-associating parameters and also for the associating parameters. Now, over the years, since '97, the soft-saft equation of state went through several iterations in order to extend the applicability of the equation of state. That includes a crossover term to deal with near critical region, density gradient theory to deal with interfacial properties, mathematical derivatives just to obtain first and second order derivative properties, such as heat capacity, speed of sound. Transport properties are also applicable through free volume theory, and of course, lastly, the polar interaction. So with this equation, we would have a holistic evaluation of all the thermodynamic properties for pure fluids and mixtures, of course, governed by a microscopic overview on the molecular system. Now, having an understanding of why we want to do this and how we are capable of doing it, we'll look at through some case studies focused on solvents for CO2 capture. Now, we need to start somewhere. And the best step for us to start is let's look at the traditional aqueous amines and let's see how we can model a CO2 chemisorption process. So in order to do that, we want to start with the traditional solvent. We want to see how we can model CO2 capture on aqueous MEA. For that, we need molecular models for the molecules that we're dealing with. We're basically dealing with CO2 that is modeled as an Lennard-Jones chain with quadrupole moment. We also dealing with water, of course, with choosing the spherical model with 4 sites, 2 sites for the hydrogen and 2 sites for the 2 electron pairs on the oxygen. And lastly, we have our model for our amine molecule, MEA. Now, what you can see with MEA is a multifunctional molecule. You would have a hydroxyl group, and you would also have an amine group. We decided to model it in a very specific way with the hydroxyl group with 2 sites similar to alcohols, and then the amine group would have 2 hydrogen, and of course, the lone pair of electron on the nitrogen. Now, we want to make the model or the approach a bit more robust and a bit more transferable without fitting a large number of parameters. So let's look at the case of MEA, how we can build a very robust model. The challenge is basically the association parameters. What we decided to do is let's transfer these parameters from, let's call it parent molecules. For example, for the hydroxyl group, we would rather take the parameters from ethanol. So we would have the association parameters for the O and H from ethanol molecule. And then for the amine group, we would take it from ethylamine, which more or less has the same type of amine functionality. Once we have these parameters that we fit the experimental data, liquid density and vapor pressure, we basically just transfer the association parameters, for the different sites that we have, and then we just plug them for the MEA molecule. Of course, making sure that the molecule cross associates for these different sites, because you have a multifunctional molecule in the sense that the hydroxyl group can cross associate with the amine group and vice versa. And at the same time, the molecules can self-associate by having amine-amine interaction or hydroxyl-hydroxyl interactions. And with that approach, we only transfer the association parameters and only limit ourselves to 3 parameters that have to be fitted, which are the non-associating parameters, M, sigma, and epsilon. We use available experimental data. The ones that you can see here are symbols for the liquid density and the vapor pressure. And you can see that the parameterization approach is quite robust. There are still some deviations at the low temperature region, but still, you can effectively model the thermophysical behavior of the pure amine with just 3 parameters fitted to experimental data. That shows that the model is quite robust. Now, we want to also deal with the interaction between amine and water, because that is our solvent that we will use for CO2 capture. In order to do that, we can also transfer the cross-association parameters between the parent molecule, which is ethylamine, and water, and effectively mimic the interaction with the VLE interaction for the VLE interaction here that you can see. We also did the same thing for ethanol and water, and this was done in a quite predictive manner. And now with these cross-association parameters, we can model the pure amine in a transferable manner, and at the same time, we can also model the amine and water mixture in a transferable manner. Now, once we have this platform, we have a robust methodology for parameterizing pure molecules and a robust methodology for parameterizing the binary interactions between water and the amine. We go back to the original question of how can we make better solvents? And the first thing that we wanted to look at is the different structures of these different molecules. And for that, we started with extending the framework to other systems. We have a framework we started looking extensively at what's available in the literature, and we had a collection of 40 different types of amine molecules. Some are primary amines, secondary, tertiary. Some are cyclic molecules with only one amine functionality. And with that database, we started parameterizing these molecules in the same transferable approach. We would take always the hydroxyl group either from ethanol or propanol, and then the amine group, we would take it from a corresponding amine functionality, either primary amines or secondary amines. And with that, we started predicting the properties of the pure amines and also the aqueous amine solvents. These predictions extend to a variety of properties. We have an accurate depiction of VLE. The lines are the predictions from SoftSAFT, and the symbols are the experimental data. And you can see an excellent correlation for vapor-liquid equilibria. Also, a good representation for density, enthalpy of mixing, which is the first derivative property. We also we also use the extended theories on the equation, which is free volume theory to predict the viscosity, and also density gradient theory to predict the interfacial tension. Also, the model showed a quite apt utilization whenever we look at blend amines, in the sense that we have a ternary mixture. You would have 2 different amines and also water. And we're showing some of these well-represented properties from density, surface tension, and viscosity. Now, with that, we have a collection of different types of amines. Let's see how we can deal with the CO2 chemisorption in these solvents, which is one of the primary challenges. What happens is that whenever you have CO2 and you have a primary amine, you would need 2 molecules of this primary amine to capture CO2, and that leads to the formation of something called carbamate. In the case of tertiary amine, you would only need 1 amine molecule to form bicarbonate to effectively remove CO2 from the flue gas. Now, how can we model this molecule? Typically, what you would do is you would require speciation data, kinetic information, and details on the CO2 solubility. So it's not only equilibrium thermodynamic, but also kinetic. In our case, we wanna trick the model and utilize an equilibrium-based equation of state to calculate CO2 solubility, specifically with chemical reactions. And the concept is basically to develop an implicit reaction scheme. What we thought about is this carbamate is basically a physical aggregation. So let's add specific sites on the CO2 molecule that can help us form these physical aggregates. In the case of primary amines or secondary amines, we would add two specific sites on the CO2 molecule. We would call these reaction sites. They would specifically and only bond with the nitrogen on the amine molecule, because this is the one responsible for the formation of carbamate. And then these reaction sites would be assigned a specific energy and volume of interaction that can be obtained from regression to available CO2 solubility isotherms. In the case of formation of bicarbonate, we would only require to add one amine molecule, so it's going to be one additional site on the CO2. And then, as I said, you would only require CO2 solubility data at a fixed amine concentration to regress these reactive sites. This is basically the approach. It has already been utilized by George Jackson and Amparo Galindo using SAF gamma Mia, and then extended by our group to different variety of systems. With the parameterization that you see here, we looked at a specific number of systems. We keep the binary interaction parameters for the non-associating parameters fixed to unity. That means we use those particular ones in a predictive manner. And then this is the result of the parameterization. For the volume of association, we decided to keep it limited to 500, which kind of mimics a very small localized interaction that mimics covalent bonding. And then one of the sites would be fixed, and then the other site would be allowed to change with temperature in a way reflecting the change in the solubility as a function of temperature. And what you can see here is with this approach, we yield a quite robust representation of CO2 solubility as a function of vapor pressure, partial pressure of the system and the change in temperature. And of course, with that, once it's fitted to a specific concentration, it can be actually utilized to other contents. For example, you see here 30 weight% MEA. It can be utilized for 15 weight%. And the same thing for piperazine under a variable amine content and, of course, temperatures. Now, the model can also be used in a very predictive manner for other properties. One of the properties of interest is basically liquidation. It helps us in identifying the amount of carbamate in the system and also the amount of bicarbonate. These are validated against experimental data, and basically we calculated from the non-bonded hydrogen segments in the association term. And you can see an excellent representation for a property that is typically measured using NMR and other experimental approaches. Another thing that we can predict is basically the energy required for CO2 absorption, the enthalpy of absorption. And you can see an excellent correlability with the experimental data over different amine loading for these different molecules. With that, we have a very functional system. Now, we ask ourselves another question, is that how can we deal with multi-amine molecules in the sense molecules that has not only one amine functionality capable of absorbing CO2, but two or three. They can be the same functionality in the sense they can both be primary or secondary, or they can be different functionality. For example, the one that you see here for TATA, you have 4 different amine sites capable of capturing CO2. 2 are primary and 2 are secondary. So can we use the model in a very transferable way? And then what we figured out is indeed we can do that. We just need to find the association parameters characterizing CO2 solubility for similar functionality. For example, we have alkyl ethanol amine, quite representative for secondary amines, and amino alcohols representative by this molecule. And what we do is basically transfer these alpha site CO2 interactions from the primary amine to represent this molecule HMDA, which has 2 associating 2 amine sites capable of absorbing CO2, and also for AEA, which has both primary and secondary amines. And just transferring these parameters from these single amine molecules was quite sufficient to actually predict the CO2 solubility as a function of temperature, and also partial pressure of CO2 in these different solvents. Now, with that, we can use the model in a very predictive manner. We can adapt the calculations for different blended solvents or even different conditions. Now, how can we use that in order to determine most promising solvents? We connect it to macroscopic calculations, specifically engineering calculations. We define a set of specific KPIs, and the KPIs that we're interested in are the CO2 loading, which is how much CO2 we can capture, and also the regeneration energy. And with that, we run the model at specific conditions, which are 313 for absorption and 15 kilopascal of CO2, which is representative for post-combustion capture. And what we see here is basically a screening predicted from the model. You have the loading on the x-axis, and the y-axis is the regeneration energy. And our preference is always in this region, which has low regeneration energy and high absorption capacity. And with that, we can rationally and quickly screen these type of solvents that show quite promising behavior, which can also be scaled to experimental measurement in a very guided and targeted way, or also used as precursors for developing blended solvents. Now, after all of this, we have some key outcomes and messages. The first one is that we have already a robust methodology that helps us parameterize pure amine molecules in a very transferable way. We reduce the number of parameters required in the fitting process to make the model as robust as possible. We have a very interesting way of tricking the model in order to mimic the CO2 chemisorption process with minimal adjustable parameters. These parameters are transferable to other amine contents or multi-amine molecules, even in the absence of experimental data. And also, when we start coupling this equation of state with a simplified engineering calculation, we can predict solvent ranking and screening, of course. Of course, this particular development in this area has been pivotal with the work of Professor Lourdes Vega and also Luis Pereira and Farid Shadad. Now, with this approach, let's actually try it for other types of solvents, something that has a different formulation or a different chemistry. Now, the second topic or the second application is basically how we can apply this to model CO2 absorption in water-free and water-lean solvents. Remember, one of the things that we talked about it is one of the problems with these traditional amines is the amount of water. Now, with that, you can look at the reboiler duty, which is the majority of the fuel cost. And the majority of the fuel cost of the reboiler duty, comes from the heat of reaction, which depends on the amine. And then the remainder is actually the heat of vaporization and the sensible heat attributed to the co-solvent. So our concept is basically, let's try to remove water and add something that has lower thermal properties from other organic solvents. Now, let's do that approach in a molecular aspect, the way that we formulated before. Of course, we have our models for CO2 and water. Now, we wanted different chemical solvents to start with. So we looked at the traditional molecules, MEA, DA, AMP, and MDA. And then we had a different variety of physical co-solvents. We have some diols, ethylene glycol, and ether functionalized ethanol. We also have alcohols and different alcohol functionalities. And lastly, some polar solvents such as acetone and NMP. You can see the molecular models and the variety of them that kind of describes different types of interactions that will have an impact on these solvent formulation. Now, the recipe is the same. We would mix our chemical solvent with a physical co-solvent. We would use the model to parameterize pure fluids if we don't have them. Luckily, we have a large extensive database of chemical solvents, and we consistently build those for physical co-solvents. We robustly validate them with different thermophysical properties. And then we also extend the interaction for binary mixtures. That includes CO2 and physical solvent and amine and physical solvent. And you can see how the model behave in a predictive manner for density, for example, whenever we have an amine and also a physical co-solvent, and also the interaction between CO2 and the physical solvent, which in some cases requires adjustment to the binary energy interaction parameter. Now, can we apply the same approach of dealing with the CO2 chemisorption to solvents that actually do not have water? The literature figured out that water is basically the best co-solvent because it has a way of activating the amine molecule in order to capture CO2. by deprotonating the amine molecule. This tendency is not exactly the same when we start having other organic solvents. They have a lower propensity of activating the amine molecule. So would the modeling approach still work and be valid? And interestingly, we actually found that the modeling approach was still valid. As long as you have a primary amine or a secondary amine, you can always use the two associating site model. What we notice is that the values of these association parameters are actually at lower magnitude compared to having the same solvent with water. But still, that reflects exactly what we were talking about, that the different level of activation is the highest with water and lowest with organic solvents. So it makes sense that we get a lower value for the energy of interaction or the energy of association. Regardless, you can see that the parameterization is actually functional. We can get a consistent behavior of the solubility isotherm at different CO2 loading and partial pressures and as a function of temperature. And of course, the same approach is extendable to other types of co-solvents. We're looking at ethylene glycol, methyl ether, alcohol, and also polar solvents. Now, the robust and accurate approach, which is very solid for us, what we want to also make it a bit more transferable. So we started looking at how can we find a correlation in order to predict these interaction parameters characterizing the CO2 interaction with the amine as a function of the co-solvent. And the best property that was descriptive of this propensity to deprotonate the amine was actually the dielectric constant. And you can see here that for the two different sites on the CO2 molecule, they correlate linearly with the dielectric constant for a consistent family, which is the ethylene glycols. We have ethylene glycol, diethylene glycol, and triethylene glycol. And the good thing is that we can use these parameters in a predictive manner in order to predict the solubility isotherm at consistent conditions and examine the behavior of these different co-solvents. And what you can see is that when we're dealing with the short chain glycol molecule, we have a higher CO2 solubility at low partial pressures, but then the tendency reverses at high partial pressures of CO2. Now, with that, we apply the same approach to different types of co-solvents, and then we can predict the solubility isotherm as a function of the co-solvent. And what you can see here is that what we talked about was actually valid from the model. Water has the highest capacity to absorb CO2 whenever it's added to MEA. The lowest was with acetone. Of course, this tendency, we're focused typically at 15 kilopascal, which is this particular region. And of course, this is a function of the dielectric constant of the molecule. We also predict the absorption enthalpy, and you can see that the highest is always with water. But then the interesting part is that there would be a second trade-off, which is, for example, let's take a look at NMP. You would have a lower solubility compared to water, but then the absorption enthalpy would be slightly lower. So that can help in reducing the regeneration energy. We look at the performance of these solvents in a comparative manner. We have the cyclic capacity at the x-axis, the viscosity at the y-axis, because water is less viscous compared to these molecules. That will have an impact on the design of the absorber. And the size of the sphere is basically the regeneration energy. And what you can see, water is the least viscous and the highest cyclic capacity, but it has the highest regeneration energy. The two promising systems are actually with NMP and methanol as co-solvents. We would lose in terms of cyclic capacity, but we would gain in terms of regeneration energy reduction. Of course, the compromise would be the viscosity when we talk about NMP, but methanol is a bit more promising. Of course, that is pending other considerations, for example, environmental performance, tendency to vaporize, kinetic consideration, but at least that gives us a direction for future research to validate experimentally and examine these systems at experimental setting. Now, another concept that is interesting is when we talk about water-lean solvents. Now, the idea would be that you would have a ternary mixture. It's basically an amine, a co-solvent, organic co-solvent, and also water in order to reduce the viscosity of the solvent itself. But we don't want to spend too much time on regressing and parametrizing. So the idea is that can we find a way to predict CO2 solubility in water-lean solvents in a very transferable manner? And indeed, we found that that is possible for us. What we need to do is basically scale the interaction parameter, the CO2 interaction parameter with the amine. That would be a function of the water-free solvent interaction energy scaled to its concentration in the solvent, in addition to the parameterized value for the aqueous solvent. And luckily, we have a big database for the aqueous solvent CO2 interaction, and we have also a data for the water-free solvent. So we can predict it for the water-lean solvent as a function of composition. And this approach was quite predictive. You can see here, for example, predicting CO2 solubility as a function of aqueous system with 70% water, and at the other end, 78% water-free with ethylene glycol, and then water-lean in the middle at different ratios of water and ethylene glycol. We also predict the enthalpy of absorption and the distribution of ionic species, which is how much of my CO2 is captured as a carbamate and a bicarbonate at a specific loading. Now, we visit another concept in the one on the quest of finding new solvents, and this one is basically changing the chemistry. We're talking about a specific type of solvent that we found interesting over the past years, which is CO2 binding organic liquids. This work we did under our PhD student, Safiq Anwar, now a postdoc in University of Guelph, and Dr. Inas Nashif at Khalifa University, also a member of Rich Center. Now, for the concept is basically, let's change the chemistry. With the traditional amines, as we've been seeing, whenever you have an amine molecule, the CO2 will be absorbed by interacting and bonding with the nitrogen in the amine functionality. And with that, you would have the carbamate as the CO2 capture species. The problem with this is basically the interaction energy between CO2 and the nitrogen. That's why we would have a high vaporization, we would have a high enthalpy of absorption. The idea of changing the functionality, we started looking at CO2 organic binding liquids. What happens here is you would have a super base molecule that is a heavily nitrogen nucleophilic molecule. This will act as the activator in the presence of an organic alcohol. And then the CO2 will actually bind with the oxygen on the alcohol molecule. And then the super base will deprotonate the alcohol, and you would have an alkyl carbonate salt. So it's an entirely different reaction mechanism. Instead of the nitrogen being involved in the reaction, it's actually the co-solvent with its hydroxyl functionality involved in the reaction. This is promising because these types of solvents, they have shown an extensive promise in terms of gravimetric capacity, and at the same time lower regeneration energy requirement, because it's apparently easier to break the bond with the oxygen. Now, can we make new CO2 balls? Of course, we would have to follow a tiny bit of a different approach. We would have to rely a bit on lab scale measurements because of some missing data in the literature. We have to build some fidelity in our molecular equation of state. Can they actually model these types of reactions and then evaluate them based on KPIs? The easiest way for us to start was to look at some traditional systems. The traditional super base is called DBU, and the traditional organic alcohols are hexanol and butanol. We started looking at different functionalities with ethylene glycol, ethyl ether, and methyl ether, because we've seen some promise for these molecules as co-solvents for water-free solvents. We formulated these solvents as binary mixtures of one DBU molecule to a different molar content of alcohol. We did some experimental characterization. We have some thermophysical properties required for building the thermodynamic model, vapor pressure, viscosity, and also some thermal stability. We're only showing the results for the 1:2 ratio, of course. And we also measured the CO2 solubility and the enthalpy of vaporization. And what we started observing that, yes, indeed, some of these systems are actually better than the traditional ones. With these ether functionalized molecules, you would have a higher, more dense molecule, a higher propensity to vaporize, which is quite negative, but at the same time, it's less viscous and it has a higher capacity to absorb CO2. Specifically when we're talking about low content of the alcohol, a ratio of 1:2. We also did some quantum DFT calculation in order to get a better insight on the functionality of these molecules and their ability to interact and absorb CO2. Also some calculations for the reaction pathway to confirm them, because some of the experiments were missing to determine the type of molecule, the type of species whenever CO2 is bonded, and of course some understanding of the reaction thermodynamics. Once we have a confidence in these type of systems, we started looking at the molecular modeling aspect to speed it up. And with that, we required, of course, our molecular models. We have an unassociated model for DBU because it's not capable of hydrogen bonding. Of course, we have our CO2 and our alcohol molecules already published in previous works. Now, without the presence of CO2, whenever you mix the alcohol with DBU, it's going to be just a neat binary mixture. And you can see that the model will quite predictively predict the density, vapor pressure, and viscosity of these solvents in the absence of CO2. The fun part and the challenging part is whenever we have CO2 in the system. Whenever we have the CO2, the bonding, remember, is going to be with the alcohol component rather than the amine component, forming an alkyl carbonate. What we decided is basically to follow the same approach of a physical aggregation process. We would add two sites on the CO2 molecule. One will form a strong hydrogen bond with the oxygen on the alcohol in order to form this alkyl carbonate. But at the same time, because it's an ionic species, we would have a weak hydrogen bond with another site added on DBU. This is going to mimic basically the interaction that we have between the functionalized CO2 here and also the hydrogen on the DBU molecule. Of course, the same parameters are regressed to the data that we collected for the solubility, the CO2 absorption isotherm, and also the ones from the literature. And indeed, this approach was quite sufficient in order to have a good representation of the solubility isotherm. The good thing that this parameter or this parameterization can be used transferably in the sense that you can use the same parameter at different temperatures. Of course, as long as the range of temperature is quite close to the one that you're parameterizing in, the difference here is basically 10 Kelvin. And the other important thing is that we can also use it for different formulation of the solvent, different content in a very predictive manner. Of course, at the end of this talk, we have showed consistently that molecular thermodynamics is indeed a powerful tool that helps in the rational design of sustainable decarbonization technologies, showcasing the case study that we had with CO2 capture solvent. Of course, these molecular equations of state, they require a very consistent and systemized, rigorous framework that can help you study the thermodynamic behavior of conventional and new solvents. Of course, you would require minimal experimental data as long as you keep the framework as robust as possible and transferable as possible. Of course, the most important choice is the tool itself. We've been showing a molecular-based equation of state. Of course, as time progressed, we started expanding the repertoire of tools that we can add. We started adding some work on Cosmo, which is basically a low-level DFT or a faster DFT calculation. We've been also adding machine learning in order to expedite the parameterization procedure and also expedite the development of different types of blends and mixtures. Of course, I want to thank Professor Lourdes Vega, which had a very prominent role in opening my eyes to the molecular thermodynamics field, and of course, all the group members in the computational modeling group. At the end, of course, we want to thank the Rich Center for the support and funding, and of course, I want to thank everyone at the Applied Thermodynamics and Molecular Simulation group, and highly appreciate this opportunity to present the work that I've been doing consistently over the past few years. Thank you very much, and please feel free to ask any questions.